Makeup artist. That's good, thank you. Looks great. Haircuts well. Are we live? Oh, hey. Hey, folks. Gee, surprised me. All right, let's play. Good morning. This one's going to be on PM measurements. These are environmental measurements of particulate matters. What I'm going to speak to is atmospheric particulates, because you could do this almost with any medium, measure the size of particles in something, right? So particulate matter, I'm going to use the EPA's own website. When you go there, you'll notice they warn you that some of their older information has been moved and you have to go search somewhere else for it. So that explains why a lot of my links that I have historically, 10 years old, have disappeared. It's not that the information's gone, it's that it's been moved and the redirects or whatever were never built to get there. So it just got harder to go find things. So this is a symptom of the internet, and it's not being as open as implied, and search engines and how they work. But that is different particulate matter, and we're going to talk about now. So particulate matter, PM pollution. I live in the Portland area. We just had some particulate matter basics with the public about a glass making facility here that went through a rigmarole. They got grandfathered in. Nobody paid attention to what was going on, and the owner certainly didn't want to, which was a shame. So what is particulate matter pollution according to the EPA? These are, the bounds of the laws that we're supposed to be using to protect the environment for all of us. So particulate matter. It's from the EPA.gov websites. I think I've got the description built somewhere else, so after this is posted, it'll come up. So again, I've got links to this. So PM measurements, what you'll see at this EPA site, if you go searching, you'll find other references with some different numbers, but basically it's PM 2.5 and PM 10. These are micron measurements, right? What's that? 10 to the minus 3 measurements? I'll get close to that. But this is what they're looking for, because these particles, we know, can get in and on lung and mucous membrane tissues and infiltrate the systems or irritate the systems. So they'll cause more mucus to be made, you cough and spit a lot, or they will be absorbed through your lung tissues into the body and possibly do some accumulation in specific organs that like that stuff. So the PM measurements in general, the real-time stuff, we get a number back in a PM 2.5 measurement somewhere, and it gets posted on the internet, and in a PM 10 measurement saying wear particle masks. You see, it's very common in Asia for particle masks to be worn, and I'm not sure how good they are at knowing what those particle masks will scrub, but you should be looking for finer than a PM 2.5 filtration for a particle mask, because the particles below that are not good. But we're measuring 0 to 2.5 parts per million sized particles, or not parts per million. I'm sorry, this is a millimeter measurement. This is the physical size of the particles. A particle that big contains, a particle that small can contain millions of atoms or millions of molecules. You can go find out how many molecules are in a drop of water. Now, a drop of water is much, much larger than a PM measurement. An example, a PM 2.5 measurement is 30 times smaller than the diameter of a hair. A hair is 70 micrometers in diameter. And we're looking for particles that are 2.5 micrometers and smaller. So that's some pretty tiny stuff. We're looking for if your hair got smashed up or damaged, or the flaking off the end of your hair. You know, the dandruff. What size is dandruff? You can ask those kind of questions. So you typically, dandruff is huge. You can see dandruff. It's a massive set of particles. So, and it's all skin. It's dead skin. There's not much life there other than whatever might be trying to eat at it. So these PM measurements are pretty specific. They are pretty exact. I mean, you know, you're measuring particles. These are, get a little ruler out and find a 2.5 millimeter. You're using a micrometer at that point. You're using something really tiny to judge, or pull a hair out. Head hair, not facial hair, because they're usually thicker. But pull a head hair out and then try to slice it 30 times with a razor blade. And one of those might be small enough to fit into a PM 2.5 and under measurement. PM 10 measurement is everything from 0 to 10, because you can't filter this stuff out. So you've got to take a PM 10 measurement, and then you take a PM 2.5 measurement, and you can subtract the two of them, but you have to do that. So PM 10 measurement would include PM 2.5s. And then there are other numbers out there. You might see a PM 20 or so. I mean, these are huge particles. Or, you know, a PM 20 or a PM 50 sounds huge, but it's still not as big as a hair. Okay, a PM 70 would be hairs. Now that might be rat hairs in your food. Okay, sorry, had to go there. So we're talking measurements. We're talking about what we measure. One more, if you look at my videos, man, I am all over the place. I'm skimming what we began learning since we started staring at the stars before we could write. That's the knowledge that got us to where we are today. That's the knowledge that helped our very elders make calendars that were good for hundreds and thousands of years. And yet they realized that those periods ended and the calendars would have to be built new depending on what the next phase of our human cycle is, not man's cycle. This is Earth cycles. So it gets pretty deep. These parts of these conversations just go into amazement at how complicated life really is. And that people know this. You know, I scratched the surface of this. There's people that have honestly delved into each one of the towers of knowledge that has built our civilization. So it's an admiration for human intelligence that I'm expressing, I suppose. You could call that an atheist faith, all right? I have a faith in humanity. Work with that. Work with that. So sources of particulate matters. Again, I'm just reading this EPA document, and it is so high level. It's on purpose high level because you need to be able to read through it and decide if you even understand these pieces of it. And it may or may not inspire you to go to the next level. And why would you want to? Well, maybe you're looking for a career. These are sciences, these are chemistry, these are physics, these are engineering. As an integration engineer, I both maintained and serviced these instruments. I worked with the chemists that did the specifications and testing and helped respec some of the instrumentation in the field through an iterative process of testing. So while I don't know the chemistry that well, I know how the instrument responds to whatever the chemistry is. And when I see things that I don't understand, I know to go find the next level of peer that I need to discuss these issues with. So, sources of PM. These are very simple instrumentations at some level. They started out decades ago as simply an air filter, a very precise sized air filter, or multiple sets of them that were run for hours or days, and someone would go out in the field and collect that air filter. They would take it back to a lab, and through a number of different techniques, including just weighing the filter itself to see how much mass it picked up. Now, in order to do weights that precise, you would have to have weighed the filter beforehand at an exact and precise temperature and humidity. And when you bring it back, because the precision you need, right, the number of zeros of accuracy you might need to see the weight of the dust contained in the filter, you're going to have to re-dry that filter, get the moisture content down on it to whatever it was when you were tested. So you could get lucky. The difference could be big enough, but that is not precision science. And we're in precisions now because of other processes that happen later. So originally these simply were filters. Somebody went out and said, okay, it's been flowing air through it for 1 week. I've got a total sample of 1 week's worth of air in the area. If I wanted to do better, I would have had to have collected that sample in a day or in hours. So now we can begin to think about how we could automate the filters and maybe move them through. So each filter section, if it was a long roll of filter material, only collected 1 hour. Or maybe one was collected 4 hours and the other one collected, so you could layer the filters. There's all kinds of things you can do to begin to get just particle size. So particle size matters. What we've done is created electronics able to measure the particle size real time, and we've decreased the measurement time rates. So where we used to have to go out daily, weekly, monthly, find a filter, replace a filter, renew and refresh things. Now we've got an instrument that just sits out there and sends us data for somebody to look at. Or more likely, there's algorithms looking for rate of change information, and they tell somebody when to come look at me. It's just a massive data set sitting back somewhere. So particulate size, that's all we've measured. I'm how many minutes into the video? All right, I'm 12 minutes in, and I've just danced around the size of the particle and measuring that particle. In old science days, all the material got brought back to the lab. Now we've got the filter material. We know exactly what that was because this is our career, this is our job, our profession, and we've got all kinds of checks and balances and bounds inside our professional work that guide us how to do these things correctly. So you're putting it all together and you're adding it up. Now I take the sample filter mass before I started collecting sample. I take the mass afterwards. Inside that filter is so many grams of material or ounces of material, or wherever country you're working in, unit of measure. Okay, you could be on another planet and call them frugons. Don't care, it's still going to be the same thing because of the physical world we live in. The next step in the lab for that would be to try to either digest, remove, or get all that particulate matter out and off of the filter material, the filter substrate, because we don't want that substrate to affect the next set of measurements we're going to take. So somehow I'm going to take all these filters, I'm going to label them very precisely, I'm going to take them somewhere else, I'm going to shake them, I'm going to drop them, I'm going to take some acid and dissolve them, I'm going to remove all the organics, I'm going to digest every molecule in there into elements as best I can. I'm going to remove all the organics so I don't blow one instrument up, and that sample is going to go to an OES ICAP system. The other sample is going to be solidified and put into a time of flight system somewhere, and it's going to look for a different range of energy levels released in a different set of particles. But those two instruments should have some hard matches on particles. I can know the substrate material, and I can subtract any substrate material that might show up in my instrumentations from the readings. Because I've prepared standards along the way, I'm keeping some pretty precise records. Now I've got elemental. I sent other parts of that sample off for organic analysis, so I didn't digest anything. I might or might not have sent them a whole section of filter for them to go and do organic sampling on it, because those are totally different rooms and assay procedures, different digestion methods if you want to remove substrate, different column materials in your chromatographs if you're doing liquid or gas spectrometry. If you're doing some type of plasma research, which that's typically ion spectroscopy, or you're looking for photon spectroscopy, chemical spectroscopy, all of these are analytic techniques we apply to it. You can see that 1 hour sample, that 1 day sample set of filters from decades ago got brought back to a lab and gets processed. The results might not come out of that lab for weeks or a month because of all the processing done. But over time, these things have gotten better. So PM measurements got specifically very much better for real-time applications. But what gets ignored is the rest of the process to finding out what is in those particulate matters. We do know if the particulates contain dioxins, so road dust, kicked up, the road was sprayed with dioxins back in the 60s and 70s, and cars drive down the road and they make dust, the dust kicks up, and you breathe that for decades. And dioxin doesn't deteriorate, we learned this. Maybe your road wasn't cleaned up because they weren't honest with you, but you live in North Carolina and it's a pretty damn nice state most of the time until a hurricane comes. So, all right, we talked about PM. I'm going to try to get 17 now. I'm going to stop at 20 just because these get too long, and that's how the real world is. So I talked a bit to PM. There's links in there. Why does it matter? Because we do measure this. There's conversations about how the EPA measures. If the EPA is only measuring particulate matters and focusing on that conversation with people, it is rather shallow. The rest of the analysis comes out in days, weeks, or months. It gets verified, and pieces of it come out in 8 different places, and who knows where the total results are from it. So yes, it's complicated. Yes, people get paid pretty good salaries for putting this information together. They get good salaries for the computer systems that support it, the decades and now, the generations of data that drives our knowledge base that has changed and added to over time. So, hey, peace out, neighbors. Another long, short one. You can't cover enough of this. You simply can't. So I'm trying to just chop up 40 years into 5 to 10 minute breaks. Enjoy the coffee. Thank you all.